theory of groups. And I think this is also a good point in time. I had given you an assignment a while ago, I think assignment 7 due 27th September it says. So obviously it has been a while since you have looked at those things. So I will spend a couple of lectures on how representation theory of Lie groups works. It is very useful, and after which we will go on to understanding the symmetry breaking, etc., the setup for the Higgs model the Higgs mechanism, non-abelian Higgs mechanism that is relevant for the standard model for the LHC. So it will become more like a particle physics course, and because it will be a particle physics course, we have to get every factor, everything right, so that we can match with experiments, and or at least try to understand what these various things look like. Okay, so what we will do now is 2 lectures I would spend on Lie algebras, and then we get back to the kind of things we were looking at, which is non-abelian gauge theories, because I realized that last time I was loosely using the word representation, etc., and I will just make it more formal. I know I have been using it all through these lectures, but I will make it much more formal right now. Okay. So already when we looked at so what we are going to do is going to do representation. So even though I am writing something very fancy, we will never go beyond orthogonal and unitary groups, because they have the necessary complexity that will capture more general things. Okay. So so when you have a group, you have some group multiplication law, let us say, which says that G1 dot G2 is equal to G3, and originally I sort of introduced the idea of representation by saying we think of a matrix realization of this. So for every, so if you give me any element G, I give you a corresponding matrix, and with the rule that if G1 dot G2 equal to G3, then M of G1 dot M of G2 equal to M of G3. Okay, and I said that this is what we mean by a representation of the group element. Okay, but we can be a little bit more abstract, and the definition of a representation is basically so the idea is to realize that matrices are nothing but are linear operators acting on some vector space. Okay. This is something which you know already from quantum mechanics. The Hamiltonian is realized as some kind of a linear operator acting on the Hilbert space, which is an example of a linear vector space, okay, with extra stuff because it is infinite dimensional, but in most of our considerations we will be thinking of finite dimensional linear vector spaces. Okay. So this M of G, so the general definition is to realize is that is a map. So a representation is a map of a group G is a map, is a linear map from G, the group G, to GL of V. This is just fancy way of saying that these are linear operators acting on some vector space V. Okay, and the G condition tells you that it has to be invertible. Okay, so it has to have non-zero determinant. So and the advantage of writing it in this fashion is that if you give me a vector, the way to get a matrix is to take a vector space, choose a basis. Once you choose a basis, you get a matrix element, or you get an exact matrix realization, but you want to write things in some way, sometimes in a basis independent fashion. So this is the basis independent way of writing it. Okay, this is how a math book would write it, but really it is nothing but in physics literature all the time we always work with specific basis. and so we once you pick a basis for this vector space, then this becomes exactly, you will get a exact matrix realization for the group. Okay. So, but the clearly the thing is that things should be things or definitions do not depend on basis, on a choice of basis. So, what this so in a physics way of saying it is that if I make a change of basis, the representation should not change even though the matrix would change. So, what happens to so under a change of basis, m of g would go to S m of g S inverse, same as for all. Okay, where S is some change of basis, and it's of course it has an inverse determinant of this thing. So, if m of g1 times m of g2 is equal to m of g3, then obviously that will also satisfy the same thing. But really, if you go back to this definition, you do not want to distinguish between these two. Okay. So, you would say that two representations are the same if there exists an S such that they get related. Okay. So, we can just define this to be m tilde g. Okay. So, if star holds, then we say that m of g and m tilde of g are the same representation. Okay. There are some other nice properties. So, suppose we are suppose you are given m of g1 times m of you are given a particular m. Let us just take complex conjugate of the whole thing, m star, not dagger, we take m star. Okay. So, okay, what I mean by that is every matrix that you had, we are you take its star complex conjugate. Okay. Now, first thing is, does it form a representation of the group? So, you just take star of this, it will nothing happens. No, we are not doing dagger or transpose, otherwise the order would change. But if you are just taking star, you can see that this also is a representation of G, or provides but now the question is it the same representation? Can we answer this question? In general we do not know, it could be, it may not be. Okay. So, we have to ask so the question to ask is it identical or same to m of g in terms of representations? The answer is yes, if there exists an S such that okay. So far we are very somewhat abstract, but let us choose some simple examples. Okay. So let us look at an example. So let us consider an example. Okay. So let us consider the following example. Consider G to be the unitary group SU2. Okay. and we look at it in the 2-dimensional representation, okay, and consider its fundamental representation. Okay. So, in that case we can write one possible choice for m of g would be e power I theta a sigma a by 2. Okay. So, I am writing out the arbitrary group elements, we have seen this already. So, now the question to ask is can, so let us look at m star, okay. What happens to m star of g? So, I star is minus I, theta a is supposed to be real, sigma a star by 2. Okay. So, what is sigma 1 star equal to? Sigma 1. Sigma 2 star is minus sigma 2, and okay. So, now the question is there an S that will relate m star to m. Okay. So, now coming back to this, what we really want, so you can see that if you look at this thing, so let us look at in some detail, let us look at this guy. So, it becomes minus I theta 1 sigma 1 by 2 minus I theta 2 sigma 2 by 2, sorry, theta plus and minus I theta 3 sigma 3 by 2. So, what we need is some operator, if I find something which will change the sign of sigma 1 and sigma 3, but not change the sign of sigma 2, I am done. Why is that? Because you can see that S m star S inverse is equal to so on and so forth. You can use the definition of e power a and you can keep putting S S inverses in between. So, you can actually go ahead and see that it sits and acts on this guy. Okay. So, now the question is, do you know any such, do you know anything, any S which would do this for you? Any guesses? Okay. Let me ask you a simpler question, something which acts on sigma 2 and takes it to sigma 2 identity, but it will do the same thing, okay, but something almost, yeah, okay. So, S, if you take S to be sigma 2, take S to be sigma 2, okay, sigma 2 square is 1, okay. So, I just leave it at that. So, S inverse is also sigma 2 itself. So, you guys should know this, sigma a sigma b is equal to 2 delta a b. So, in particular sigma 1 sigma 2, okay, plus sigma 2 sigma 1 equal to 0, for instance. Okay. So, I can multiply from both sides. So, sigma 2 sigma 1 sigma 2 is equal to minus sigma 1, because I have to take it to that side. Similarly, you can see that sigma 2 sigma 2 sigma 2 equal to plus sigma 2 and sigma 3 sigma 2 sigma 3 sigma 2 for the same. So, the S should be just sigma 2. So, what can we say about this particular representation? The fundamental representation, which is 2 dimensional, is the same as its complex conjugate representation. Okay. So, the statement is, so one usually writes 2 for the representation, we say that 2 equal to 2 star. Okay. I mean, now you may question which should I call 2, which should I call 2 star, that is up to you. Okay. If you call one of them 2, the other will be called 2 star, but here it does not matter, they are related to each other by a similarity transformation. You could not have guessed it just like that. Okay. So, now it looks very tempting. What about if you replace this by SU2 by SUN? Okay. Will it hold? Okay. So, I have given you a case where in fact m equal to m star. So, now the question is, let us consider, let me another example. Or actually examples, it is an infinite family of examples. So, we consider G to be SUN and M of G. Now, let me just be very, so let us choose M of take G to be SU3 and we can write this as some e power I theta a lambda a by 2, and in that assignment these lambdas, so a runs from 1 to 8 in this case. Okay. And so, this will be, and lambda is are the Gell-Mann matrices. One thing which you might have appreciated from looking at the assignment where these things were explicitly written out was it was souped up version of the Pauli sigma matrices really. Okay. Especially if you looked at lambda 1, it was just it was lambda a, first a was just half rather sigma a with 0 0 0 0 0 at least for the first 3 guys among other things. Okay. So, now you can ask what is m star of G would be okay. So, that is one, the first 3 guys if you look at them it is exactly like that, and so it will give you some insight into what S could be. Okay. Sorry, m star, and you can go back and play with it and see if you can find one. The answer is no. Okay. Here yeah, you need this is the most important thing, it is the same as for all group elements here. So, for it was independent of the value of theta, it did not depend on theta, because even out here if I just switch on only first 3 thetas, then it is the same as SU2 and then you can map it, but that is only a subset of the it is only a SU2 subgroup of SU3. So, there are a whole bunch of elements which are not of that kind. Okay. So, here is an example where the complex conjugate representation is a representation of the group, but they are not the same. Okay. In fact, more generally n is not equal to n star for all SUN for n greater than 2. So, this is actually the more generic case, not Okay. But there exist representations of SU3, okay, for which that is true. In other words, there might be something else which is say 6 dimensional or 8 actually 8 dimensional, yeah, 8 dimensional guy for instance. Now that would be real. There exists an 8 dimensional representation called the adjoint or whatever, that is real. So if you find a representation which is like this, you say that the representation is real, okay, and if it is like this, you say that it is not, it is complex and not equal to n star. Thank you. Is this clear? Okay. Yes.
It's a linear map from the group elements to images. Where does the linear part come in? What do you mean by linear map there?
Oh, so a linear map. So a map is linear. Of a vector space to the vector space is linear if, okay, a map L, let us say L of this is what one means. Yeah, wait. So first let us understand a linear, this is what we mean by a linear map, or okay. So once you have something like this, what if you have a map which is linear, then it suffices to look at the basis elements how it maps. So let us say that you choose a basis for V, which is say EA, this is a basis for the vector space, then this linear map can be written as a matrix, because you just say that L of the basis vector should be L A B E B. This is some vector, any vector can be expanded in that basis vector. So usually, so this is the matrix or the matrix element as we would write in quantum mechanics. Okay. So every linear map gives you this thing. Okay. So here you go back to this group, for every group element I give you a linear map, the map changes, okay, but that is the matrix. So L A B or M A B I shall call it. So this would be the matrix element. Okay. So the matrix M I would call as equal to this, the set of these guys. Are there any? There is one more important idea which again you may have seen, we have discussed it in specific examples, about the idea of if a representation is reducible. Okay. So we say that a representation actually, before I discuss this, you notice here I am looking at Lie groups, and you can see that if you pick your group element in some representation, the Lie algebra guys also come as some matrices. Okay. So yeah, there is a direct connection between a representation of a Lie group and the representation of the Lie algebra. So if you give me a 3-dimensional representation of SU3, then by considering infinitesimal group elements, then I can get the analogous Lie algebra value. Or we can be even more, this thing you take d by d theta a of this thing and set theta equal to 0, then it will pull down exactly lambda a. Okay. So the thing is that we can talk of even representations of Lie algebras. It is very obvious. I mean, again, for every Lie algebra element value, you will give me a matrix. Again, it is enough for the same argument, which I had out here. Again, it is enough for me to give you how it acts for the basis of the Lie algebra. Okay. So in this case, the basis is the Gell-Mann matrices. Okay. So a representation of a Lie group, no, not necessarily Lie is not so important in this, of a group is said to be reducible So, a representation V. So, usually the vector space itself is called the representation. The representation V of the group G is said to be reducible if there exists a G invariant subspace. Okay, if you give me some vector space that there is something of lower dimensionality, notice I am not saying equal to, it is a strict subset. So, something which is lower in dimension. Okay. So, what that implies is that we could go ahead. So, let us say that we have a bunch V1 to, let us say we have an n dimensional representation. There exists a basis where, let us say the first m of them, they let us say they span W, this whole thing spans V. What it says is that this matrix can be written as a block acting on this. So, I am just writing this as M1 of G, M2 of G, and I am just fixing the zeros. Okay, 0, and this could be non-zero. Okay. So, what this tells you is that the first under the, if it were in this form, M1 of G would only mix the first m components for all G, okay, and not mix it with this thing, but it does not tell you, I mean you could have a bad situation where these guys actually mix with this. Okay. But quite often we will come across situations where even this star is a 0. Okay. So, so the question is, but of course it need not come in this form, because I can always make similarity transformation and make it look messy. Okay. So, it is only a sort of this thing that you should find, I mean just because you find that in your presentation somebody gave you a bunch of matrices, it did not look like it had this block diagonal form. Okay. And then you should not let yourself think that it is irreducible. Okay. If it does not have any G invariant subspaces, then you would say that it is irreducible. Okay. In some sense the irreducible guys are the building blocks. Okay. So, we will look at only situations where it is truly nice. We will say something like this, we will call this, then we can call this W1, we will call this W2. So, we write V as okay. This is just the usual direct sum of vector spaces, which is just the fancy way of saying you take certain bunch of guys, put them and put the other things together. Okay. So, yeah, we cannot write it as a direct sum. One of them is irreducible, it could be, yes, but we will always we will never look at quite often in all these examples we will not have the bad, we will not be looking at situations like this, we will look at nicer things like this. We have actually seen this before once, where we found that we could find some change of basis, and that was in the case of orthogonal groups. Does anybody remember that? We looked at second rank tensors. Exactly. So, in that case when we took a second rank tensor, it had in 3 dimensions it had 9 components, and I pointed out that we could break it up into 6 plus actually 5 plus 3 plus 1. 1 was the trace part. So, these never mix with each other. So, that is the case. So, in general this kind of thing could happen, and it is all mucked up or messed up by the fact that there could exist a similarity transformation which would this thing. So, the goal in general is to, given a group, construct all irreps of the group, irreducible representation. That means it is something which does not have G invariant subspaces. Somewhere there will be one group element at least which will mix up everything, you can never find. Okay. So, you cannot break it up into a smaller part on which you have an action. Okay. So, this is the thing. for finite groups actually there is a lot of nice structure. First thing is the number of irreducible representations is finite. In fact, there are some nice number theoretic stuff you will have. For instance, you can yeah, I think it is like this, dimension of the group for finite group, this is equal to, I think, the sum of the dimensions squares of the, if you something like this holds. Okay, so if you told me that there was a group which was 6 dimensional like S3, okay, then what are the representations it could have, whatever. So you have to break it up into number of squares. So how can you break up 6 into sums of squares? It can be 1 square 6 times, it can be 1 square plus 1 square plus 2 square, it can't have 3 square. Okay, so that would tell you that so 6 equal to 1 square plus 2 square, 1 square plus 1 square plus 2 square. Okay, this is some nice stuff you can do, and you can prove. And so in fact for S3 this is what happens, it has 2 one dimensional representations and 1 2 dimensional representation. Okay, but we are not interested in finite groups, so we will be looking at continuous groups, and this is not true. Okay, and so the, like I told you long ago, that finite groups are fun because you can do a lot of explicit things with them, and here is an example of them. It does not matter if there is a group like the monster group which has 10 power 53 elements, okay, but people have been able to construct its character table. In other words, they are able to construct all representations of that, because as somebody put it, is 10 power 53 is a finite number. Okay, I think the number is correct, but so even though it is such a huge thing, you can still sit down and do it. In fact, it has only 26 irreducible representations. Okay, so but coming back to this, we are interested in finite, not in finite groups, we are interested in Lie groups, which appear a lot more in physics, though in condensed matter physics, if you are doing crystals and stuff like that, finite groups do appear in that context. So the idea here is to sort of see how to go ahead and construct this, okay, and we will sort of do this for SUN, and then I will wave my hands for the orthogonal groups, and then leave it as a homework exercise for you to to work out for all the other groups. Okay, so let us revisit. We start with SU2, which we think we understand because we see it in quantum mechanics all the time. And so let us look at representations of SU2, the group, or we can even say the Lie group SU2. Okay, yeah, there is one more bit I forgot. I mean, so the term which will also require that the linear map be unitary. So okay, that will be an extra condition. It is not an arbitrary general linear transformation, but it is a unitary transformation. Okay, and so in physics we are usually interested in unitary irreps of Lie groups. Okay, so if you are so what we mean by this is M of G, the matrix, should be unitary. Okay, it also is equivalent to saying that the Lie algebra element should be Hermitian if you put an I out here. Okay, also if we write G as some e power I theta a T a, so rather M of G is this, and this will write I will use the same letter T a, even though I should write M of T a. Okay, or maybe I should. Okay, so if this is unitary and we take the parameters to be real, then this will be Hermitian. Okay, for the Lie algebra. Okay. So, this will be the condition that will, if you put in unitary. Irrep is already something. So, we need to classify these things. So, the answer is known for SU2. So, what we will do is we will solve a lesser problem, which is to actually look at Lie. The reason to look at Lie groups is that it is enough for us to look at the Lie algebra elements, and that is all we will do. Okay. So, let us remember certain things about SU, the Lie algebra SU2. So, this is what it satisfies, and we have to find different matrices which satisfy this sort of a thing. Okay. And so, the way we will do this is to rewrite this thing as follows. Let us define T plus minus okay. So, these are what you would have called the raising and the lowering operators, okay. And we have T3. So, if we write out the various algebra, so let us look at, for instance, T1 plus minus I T2 with T3. So, T1 with T3 will give you minus I T2, and T2 with T3 will give okay. So, this just becomes minus or plus T1, is this correct? Okay. So, I just wanted to work out this. So, this implies okay, because I never remember the okay. So, this is a non-trivial commutator, and so this does not make use of any details of what matrix we are using. This is true for in general. Okay. So, what one is doing, the reason to change into this is what we are doing is taking the Lie algebra and writing it as a bunch of, it is a direct sum of 3 parts, okay, which is exactly this separation. So, in this case I will just define T plus belongs to this, T3 belongs to this, and T minus belongs to this. Okay. They are all subalgebras, in the sense that if I take T plus and take its commutator with itself, I get 0. It is a trivial sense in which it is a subalgebra, okay. And T minus is also subalgebra, and T3, each one of them are one dimensional. So, they will all form a closed subalgebra. What we will do in general is to break up all the generators into whatever, like the raising, and we will call this the raising part, the lowering part, and this we will call the Carton sub algebra. Okay. So, this is the standard split. The reason I am sort of writing this out is to show you that this generalizes to all other Lie algebras. We will see it in more detail in other cases, but the key point here is to do this. And so, coming back, let us look at some details. For instance, if you look at, let us take the case when m of T A is just half sigma A. Okay. So, if you look at m of T3, this is the 2 dimensional thing, it would be plus half minus half. So, this is a diagonal matrix, okay. And what is m of T plus? It should be what? Sigma half of Okay. So, you can see that M of t plus is upper triangle, the other one is lower triangle. Okay. So, this is something which we know, but we could I claim that we can recover this in a very nice way without even by using this kind of decomposition, and the way it goes is the following. So, we will start with, so what I am going to do here is to construct for you a vector space, and the way I will construct the vector space is to start with one basis vector and keep constructing the other guys, and at some point I will get all the full all the guys in the all the basis vectors of the thing, and it may terminate, it may not terminate, it depends. Okay. So, we start with something, so we start with an element. So, let me start with so in this for this example we will just start with the usual state, which is m equal to minus half. I will use the Dirac notation, the Ket notation, okay. And just for completeness I will just write this. This is the j equal to half, m equal to minus half state. And what is the property of this? If I try to lower it further, so for the rest of this thing I will just not use m of t plus, I will just use t plus for m of t plus. Okay. So, what we know is that if we try to lower it further, what happens? It is 0. Okay. So, we start with some guy which is such that t minus on that is 0. Okay. Then we act on it with t plus. And this m eigenvalue is defined to be T3 of the same thing, but this is not going to be 0, but then we can also show that t plus t minus is T3. Okay. So, you can show that this m equal to plus a half. Okay. Now, we can, but nothing tells me that I cannot go on further. So, I should proceed further. Let me take one more. So, I do t plus square Is this possible? No. Okay. So, but this is supposed to be 0. So, how do we show that something is 0? If you have a unitary system, a nice positive definite vector space, okay, what would you say in such cases? If something is 0, that is equivalent to it having 0 norm. Okay. So, what you can do is you do not prove that. So, you prove, one shows that this vanishes by considering its norm. Okay, and then it implies that you will get 0 norm, and that implies that it terminates. Okay. So, I need a little bit of definition. So, first thing is that I should define for you what is the Carton sub algebra. Okay. So, let me define that. Okay. It is the maximal commuting set. It is the maximal So, in other words, you take any Lie algebra element could be taken and that will commute with itself. Then you look for among the other generators, is there some other linear combination which will commute with this, keep on doing it till you get all the possible generators. So, you come here, I chose T3 to be in it. So, now you can ask, can I, there is what else remains, there is T1 and T2, T1 does not commute, T2 does not commute with it, and no linear combination you can convince yourself commutes with T3. So, it just tells you that for SU2 you will find that there is only one such generator. If you go to SU3, in this example which we looked at, if you look at the Gell-Mann matrices, you one of the natural things is lambda 3 and the other one is lambda 8. Okay, those are the it is only conventional, by the way, I could have chosen some other thing. Okay. So, even here there is nothing which tells me that I should have chosen T3, I could have chosen T1. Okay, there is nothing, it is not unique, but what will be unique will be how many of them you can choose. Okay. So, the number of such the number of generators is called the rank of the Lie algebra. Okay. So, what we see is that rank of SUN turns out to be n minus 1. Okay. So, for n equal to 2, which is SU2, there are 2 generators, for SU3 there are 2 generators, so on and so forth. Okay. So, once you have maximal commuting generators, you can see that you can simultaneously diagonalize them if you have some matrix. Okay. So, implies that acting on implies M of T A can be simultaneously diagonalized. By some S. We already saw that if we make a similarity transformation, it is the same representation. So, I can always adjust it such that I go ahead for all T A in belonging to the Carton sub algebra, only those I can. Okay. So, these become diagonal, but another way of saying it is that we can label every element basis vector of the vector space by the eigenvalues. Okay. In other words, every basis element of V is labeled by R numbers corresponding to the eigenvalues of the Carton generator. Okay, R is just the rank of the group, Lie group. So, what it means, so in this case, coming back to this thing here, T3 was diagonal. It told you that in this, of course, you have to work in the you have to figure out what the S is and diagonalize it, only then you get a natural basis which is 1 0, the natural one to that this thing. So, here you can see that the vector 1 0, which is 1 0 has eigenvalue half, and the vector 0 1 has eigenvalue minus half. These are the two m equal to plus half and m equal to minus half states. Is that clear? Okay. So, obviously, if you have n minus 1 of them, there will be n minus 1 labels. Okay. But remember, the representation is the full vector space. Okay. But each of these elements will pick up some labels. Okay. So, what so the first step here is to realize that in a matrix realization this is diagonal, you achieve that, but what about L plus and L minus? It is really this one. L plus you can think of them as upper triangular guys and L minus as lower triangular guys, and you know that under matrix multiplication upper triangular matrices remain upper triangular, lower triangular remain lower triangular. So it is really that is the idea in this separation. These are like upper triangular, diagonal and lower triangle. So I think some of you would have done numerical methods course, right? It is called some UDL or something decomposition. So what one is doing is the UDL or the LUD, is it called LUD? LUD decomposition. Okay, so L, okay, how does it go? LUD, okay. So this is really glorification of that. It is really the LUD decomposition. That is what you are doing, okay. And but doing it in the abstract first. You have a Lie algebra with structure constants given to you, you can always break it, you can always bring it to that form, okay. So now let us see how we would do arbitrary. So let us now we hopefully we understand this decomposition of the Lie algebra, number one, but and we also understand one simple example of this thing, okay. So now the question is, what about the other representations? We know that there are these spin j representations which have 2j plus 1 dimensional representation. How would we go about constructing that? Actually the procedure is really the same. You start with something, we will call it the lowest weight vector, and since it is lowest, let me put it the lowest weight vector, that is the lowest of my thing, with the such that t minus on that is 0, okay. And it has to have some label, so we will just call it that label. I will call that label, I will just call it minus, that is the m label, so I will just call it minus j, okay. At this point j is just a number, I just say that T3 of minus j is equal to minus j times T3, okay. I do not even assume that j, I do not have to assume that j is integral, half integral or anything, I do not make any assumption. I just say that this thing is that way, and I have to introduce a norm. I assume this is normalized to 1, okay. It exists. So then I start raising it, so I will do t plus of minus j. We know that this is proportional to minus j plus 1, okay. You keep on doing this, you will keep raising the what you are doing is raising the m eigenvalue. So it is like a raising operator, okay. And each time it only gives you proportional to, you have to work out the norm. So you need to check out the norm. This will terminate okay, if and only if j belongs to at some point you let 0. Now you can ask, suppose j is not this, let us say it was irrational, okay, then you will find that this will never terminate. If this is so j plus 1 whatever, it will keep going, it will go off to this thing. If you work out the norm, you will start getting states which have negative norm. It violates the fact that you want a unitary representation, okay. So unitarity, else. So here something nice happens, it hits 0, and if you still say I do not care about 0, you ask what happens about the next guy, it will be negative, but at least I can consistently truncate it by saying that whenever it hits 0, it is the I do not proceed any further, that is my 0, it stops, okay. But if j were not belonging to half integral values, then there will be states or vectors rather of negative norm. So, if you do not care about unitary reps, you can construct these guys, and there is no reason for it to terminate because it is never hitting 0. You will get end up getting infinite dimensional representation. So, there exist infinite dimensional representation. In fact, I have given you an infinite dimensional representation. If you take J to be anything, by hand you can construct an infinite dimensional representation of SU2, which is not unitary. So, this is not something I am going to prove, but this is a theorem. So, what you do in general is analogous to this. You will have a bunch of eigenvalues, as many as as the rank of the group. Okay, so you will write something like this. So many labels, and there will be these, each one of them will be the eigenvalues of some Cartan generator, and then you just say that the analog of L t minus equal to 0 is to set all the generators of L minus should be equal to 0, and this is consistent because if you give me 2 elements, if I take its commutator, that is also in L minus, it is a closed sub algebra. So, it is more than one conditions. So, example would be in SU3 it has rank 2. Okay. So, conventional things is to choose, for instance, let me write out in terms of the, so one defines TAs to be half. So, I am writing it out in the 3 by 3 representation, but it is true in general. These, I mean, you can think, you can abstract away in terms of the Lie algebra what it does. So, let me define T plus minus to be okay. So, if you look at this, this is just exactly like you did for SU2, because it is an SU2 sub algebra. So, these are standard conventions which people have. Okay. So, T plus, U plus and V plus. So, and you choose T3, and usually there is some Y generator which is some factor which I never remember, 2 by root 3. Okay. So, this is H. TUV. So, 8 generators, I have broken it up into parts. Okay. You can go back and look at the in terms of the Gell-Mann matrices, you will see that these become upper triangular, these become lower triangular, and of course, these you know already that they were diagonal. Okay. This 2 by root 3 stuff has to do with Y being related to something called hypercharge. Some of you are doing particle physics, right? You would have seen that maybe. Even if you have not seen it, you are going to see it in this course later. Okay. So, I have to be horribly explicit here, but you can see that these generators, this decomposition holds not just when a TA equal to half lambda A, it holds in general, because this is a faithful representation of the Lie algebra. So, now coming back to this, so this condition L minus would tell you that T minus, U minus and V minus will annihilate this. But now comes the problem, we have to raise things, but for raising I have how many possibilities? I can raise with T plus, I can raise with U plus, I can raise with this thing. So, it is like now a tree, and they do not commute with each other. Okay. So, you have all these weird things which you can do, and in principle it is the same as this, and every time you hit a 0 you terminate things. So, you put a cap, and the non-trivial statement is that the representations of SU, unitary irreducible representations of SU3 are finite. Okay. In other sense, whichever way you did, I can start first with T plus and then operate with U plus, etc. But of course, using the Lie algebra you can prove that something else they could get related, you could be 2 different paths could lead you to the same guy. So, you have to work with all these things, and you will get this, you start with this and you terminate it. Okay. And so, you get a whole bunch of representations, and this is just an algebraic way of saying how the representation is constructed, but you can see that beyond SU2 that is not the way to go. I mean, it is pretty hard to do it, and this is not the way we will construct it, but conceptually it is important to realize that it does not matter if your thing is finite dimensional or infinite dimensional, it does not matter. Just about all of the, whenever your Lie algebra admits this decomposition, you can always do this thing and put this condition. Okay. I could have equally well have started with so this is like starting with a bottom and showing that there is a roof, okay. But I could have started with plus j, defined my highest weight state as t plus annihilating everything and doing the lowering with t minus. So similar things can be done out here, but when you have a situation where you have both a roof and a ceiling, it does not matter which way you start in some sense, okay. But there could be situations where there is only a roof or only a ceiling, okay, and they will give two different kinds of representations. So I am but if you are looking at just the normal orthogonal groups, unitary groups and these things, all these things are finite, they end up with situations where the unitarity constraint will give you only finite dimensional representations. Of course you could say that j going to infinity, but in some sense, you know, it is a limiting case. So but typical representations for a given j are finite, so it terminates, okay. In some sense there is one more example we know which fits into this sort of a setup, which is the Anglo momentum algebra. A dagger equal to 1, okay. A square is 0, so you can think of a, so so you would say that a on 0 is 0, this is how you define it, and you this one as norm, and then you keep raising, but this is a case where there is a floor but no ceiling. A dagger will keep going all the way through, okay. Now you may think, well, there could be one more state which is a dagger acting on something equal to 0. Why do not we consider such states in quantum mechanics? I could have, like I said, you know, I could have considered something like this. So let us call this, okay. Yes, actually no, you work out, go back and you know this thing in terms of realization in terms of x and p, you solve the differential equation, you will find that this thing is its x space representation would be, if this is is Gaussian, this would be e power plus x square by 2. So it is not in L2, it is not in your Hilbert space, it goes out of the space. So that is why you do not consider this. But in the abstract setting, which is the way we are doing it, this is also possible. So now you can see there are other things which will come, and so unitary irreducible is a pretty interesting this thing, and you can see that this also unifies just the harmonic oscillator and the Anglo momentum algebra. These are the two algebras which we use quite a bit in quantum mechanics, and the neat stuff is this actually covers not all the Lie algebras require only these kinds of things, okay. And that is why I am sort of giving you this abstract thing which you can never ever really use it to construct things, but it is a conceptually useful thing. So next lecture what we will do is we will see how to actually construct things, and it will be the tensor method or whatever. There will be nice ways of constructing irreducible representations of SUN.